Hi, good evening. Can you hear me, Sandeep? Hello, Sandeep, are you there? Hello, Sandeep, are you there?
Yeah, I am here. Can you hear me? Yeah.
Yeah, I can hear you. Okay. So I need to start because it's already 6 p.m. So yeah.
Okay.
So in this session, so by the way, just tell me one thing that in the NPTEL session, I mean the search class, has he done the subsequence thing?
Actually, I have not heard the week three lectures.
Okay, okay.
Sorry.
No,
Yeah.
so, so
Yeah.
up to week two, what has been done?
Yes. So let me see. Actually, so you can concentrate on MSc students. I am a PhD scholar.
Okay, okay.
Okay, you can concentrate on them maybe.
So there is another student named Sneha. So are you a MSc student?
No, I'm actually pursuing my BSc.
Okay, okay, then good. So can you tell me what has been done in the search class in second and third week?
Sir, actually, this is my first class which I'm joining, the
Okay.
sessions.
Okay, okay. I understand. No issue. So, so one second. So have both of you done a sequence? I mean, have you read it before? I mean, of course, the PhD, the Sandeep has you read it before. But Sneha, do you know about sequence?
Yeah. You can ignore me. So
Yeah.
yeah.
So Sneha, do you know
So
about
I'm just
sequence?
here for the ending portions. That's all.
Sneha, do you know about sequence?
Yes, I have a brief idea.
Okay, awesome. So yeah. So today let's start with the subsequence. So well, this will be a 2 hour session, and if you have, I mean, any confusion or query, you please ask me. I will try to clear as much as possible. Okay. So um, one second. Can you see the screen?
Yes.
Okay. So do you heard about subsequence or do you know the definition of it?
No.
Sorry, well, please be louder.
No, sir.
Okay, okay. So, suppose UN be a real sequence. By the way, should I make my handwriting a bit large or is it okay?
It is all right.
So, suppose UN is a real sequence and let Rn is Rn is a strictly increasing sequence of natural numbers. That is the sequence R1 is that is R1 is less than R2 less than R3 less than is strictly less than. Then URN, that is U suffix R suffix N, is known as subsequence of UN. Okay. So what is basically saying? It is saying nothing but suppose we have a sequence U1, U2, U3, U4 dot dot dot. So moral of the story is any subsequence of this given sequence UN will be U1 like U3, U5, U4, U6. So it will be some terms when it will be like alternative terms you can take any number of random terms but in increasing order of index. That's the subsequence. That's it. For example, suppose we have a sequence 1 by n. Okay. So it's look like what one half, one third, one fourth dot dot dot. So one of the corresponding subsequence is one, one third, 1/5, 1/7, dot dot dot. And another corresponding subsequence is 1, 1/2, 1/4, 1/6. This is another type of sequence. Sorry, subsequence. That's it. So we can choose there can be infinite number of subsequence because this Rn is strictly increasing sequence of natural numbers. So there can be infinitely many type of subsequence. Okay. So so there comes a theorem comes there. Okay. This theorem tells that the theorem tells that suppose un is a sequence converging to L if and only if all of its subsequence converges to L. This means what? Intuitively, suppose this is L and we can choose a very small epsilon neighborhood. So, okay, first let me read it out, the theorem. The theorem says that if you have a sequence un and which converts to a particular point small l, then all of its subsequence converges to L, and conversely, if all of its subsequence converges to L, then the sequence even will goes to L. Okay. So this directly tells that if we have a, I mean, we can, if we choose a small epsilon neighborhood around L, then obviously this L will contain some point of un after some k, like this is un naught plus 1, like un naught plus 2, something like that. So this theorem tells that obviously around L we can get a subsequence. We can, I mean, now the point is that since the all the subsequence are of the form, I mean, yeah, the subsequence are URN form, right? And since Rn is strictly increasing, so anyway, it is obvious that Rn is greater than equal to n, right? Just observe it. That Rn is a strictly increasing sequence of natural numbers. So obviously Rn is strictly greater than equal to n, right? Is it okay, or is there any confusion? Anybody? Okay, so I think everything is okay. Everyone is okay with it. So Rn is greater than equal to n. So basically, what we can intuitively guess is that in between these portions, we can find the subsequence urn. So this all of the subsequence converts to L, and converts is a theorem. But the thing is, here in this session, the main motive is to solve the problem. So I am assuming this theorem that a sequence converges to a particular point L, if and only if all of its subsequence converges to L. Okay. So let's see an example. So find the limit tending to infinity 1/1/2 and whole to the power n is what? Well, now here we need to use the concept of subsequence. So we first consider the sequence 1 plus 1 by n whole to the power n. We know that this sequence converges to point E. So now observe that 1 by 1 plus 1 by 2n whole to the power 2n, this is a subsequence of 1 plus 1 by n whole to the power n, right? So this subsequence will converge to E. This implies what? This implies 1 plus 1 by 2n whole to the power n is equal to E. But we need to find 1 by 1 plus 2n, sorry, 1 plus 1 by 2n whole to the power n. So the limit of 1 plus 1 by 2n whole to the power n is equal to root E. Okay. Does everyone understand this method? It's just nothing but using the first theorem, which says that since we have a given we have a well-known sequence 1 plus 1 by n whole to the power n, which converges to a particular point E. So the subsequence 1 plus 1 by 2n whole to the power 2n, this subsequence will converge to E. So the desired limit is root e. Okay. Everyone understand this?
Yes, sir.
Okay. So, let's see. So there is another example which tells us show that the sequence minus 1 to the power n is divergent. So can anybody tell how to show this? The sequence minus 1 to the power n is divergent. How to show this? Remember that we have the following theorem, which we have seen at the beginning, that if a sequence converges to a particular point, if and only if it's all of its subsequent converges to that point. Okay. So now, once again, someone is trying to join. So, so can you tell me how to show this sequence minus 1 to the power n is divergent? Well, so so let's say how to apply that theorem. Observe that the even subsequence is only consist of 1, and the odd subsequence consists of minus 1. So the even subsequence goes to 1 and the odd subsequence goes to minus 1. So I mean, if the sequence minus 1 to the power is convergent, so even sequence odd subsequence must goes to some unique point. But since it is not the case here, so the sequence minus 1 to the power n is divergent. So yeah, that's it. And yeah, there is another theorem which tells that so it's a theorem uh, which tells that if un is a sequence of real numbers and if limit n tend to infinity u to n is equal to L is equal to limit n tending to infinity u to n minus 1. That is, if the even and odd term will converge to a same limit, then the sequence un converges to L. So it's a theorem. So how to prove it? So choose epsilon greater than 0. Now since un converges to L, so obviously u2n minus L is less than epsilon for all n greater than or equal to k1. And since limit n to infinity u2n converges to L, and since this odd sequence limit converges to L, so this implies mod of u2n minus sorry u2n minus 1 minus L this is less than epsilon for all n greater than or equal to k2. Okay. So if we choose k is equal to max k1 k2, then the first sequence holds for all n greater than or equal to k, and the second inequality holds for all n greater than or equal to k. But since it's an odd term sequence and even term sequence, so together it will give all terms of the sequence after the point k. So together this gives mod un minus L less than epsilon for all n greater than or equal to k. So what I've seen that if un is a sequence of real numbers and if even term and odd term converges to same point, then the whole sequence converges to same points. So in this way, I mean, yeah, in this way we can use this type of theorem. So does everybody understand the proof or any confusion? Tell me. Any confusion? Okay, so I think everyone is okay.
You can go ahead.
Okay, okay. So, uh, for example, yeah. So consider. So by the way, does everybody know the monodon convergence theorem? Well, so one second. So monodon convergence theorem tells nothing but suppose un is a sequence of real numbers and assume un is bounded above. So this theorem tells that if the sequence un is monotone increasing, then un is convergent. Okay. So this is monotone convergence theorem. Which tells what? This tells that.
I have a problem. Can I ask?
Yeah, sure.
Yes, it was given that there are two sets A and Y. X is being mapped to Y, and A and B are subsets of X.
Wait a second. Suddenly, from which topic you were asking?
Real analysis. That it was given as a question in the assignment which we submitted. The last date was yesterday, so I am asking.
So the date has been covered.
Yes. It
Okay.
was last day was 8. Today is 10.
Yeah, I understand. Yeah. Now tell. Yeah. So what is the question?
It was given that there are two sets X and Y. X is being mapped to Y. Like f is a function from X to Y, and there are two sets which are A and B, which are subsets of the set X. So is it true that f of A intersection B is equals to f intersection F?
No, not true.
Yes, but why? Can you please say?
Yeah. True. I mean, it is. I mean, we can find a counter example. In this sense, it is not true. It is not always not. It is not like that. We can find counter example. So consider the following. One second. So this is our x and this is our y. So this is 1.1, 2, 3, 4. Yeah. And A, B. So 1 and 3 goes to same point. 2 and 4 goes to same point. Okay. So now choose A to be 1 and 3. Sorry, choose A to be 1, 2 and B to be 3, 4. So the A intersection B is empty, right? So f of A intersection B empty. But what is f of A? F of A contains the points A comma B, because f of 1 is equal to A and f of 2 is equal to B. And what is FB? FB is again A comma B, right? So FA intersection FB is A comma B, which is non-empty. So yeah, this is the counter example. So what we have done, we have choose take x we have chosen to be 1 2 3 4, and we assume that f of 1 is equal to A is equal to f of 3, and f of t is equal to f of b is equal to f of 4. So with this choice of A 1 2 and b equal to 3 4, we can see that f of ab is intersection, f of A intersection b is empty, but f of A intersection f of b is singleton A, I mean doubleton A comma b. So I mean, so it is not true, right? But you understand? You understand?
Yes, I got it. Thank you.
So
And sir, where can I get this recorded lectures?
from NPTEL, I mean, they will share the video, I guess. Yeah, they will share the YouTube link. Okay.
Yes, sir. Thank you.
Yeah, you can ask the Bharti ma'am. So we are in the model confidence theorem, which tells that suppose U1 is a sequence of real numbers and assume that U1 is bounded above. And suppose we are given that UN is a monotone increasing, then UN is convergent. It's a theorem. So now we are not going to prove it, but we are going trying to get some kind of intuition. So how to get it? So we have given that UN is a monotone increasing. So suppose this is U1, this is U2, this is U3, this is U4 dot dot dot. But it is also given that UN is bounded above. So assume UN less than or equal to capital F or some M. This is our capital M. So and assume that this is the, I mean, since not only bounded above, so we can assume this is the supremum. Okay. So now since this is a supremum, so and even is increasing, so all even will go nearer to the capital M, but it can't cross capital M. So all even will be just left portion of the capital M, but very close to capital M. So even tries to tend towards M. So this, if M is upper bound of this even, then even converges to capital M. This is known as the monotone convergence theorem. Okay. So let's look at some kind of examples. Yeah. So suppose we have a sequence E1 and defined by E0 less than E1 less than U2, and also given UN plus 2 is equal to half of UN plus 1, n greater than equal to 1. So we need to check that this is convergent. Okay. So those who have attended the last session, they might have seen this problem. We have solved there in using very basic approach, but here we will use the concept of subsequence. Okay. So just look at the, first of all, look at the sequence E1, how it looks like. It is given that E1 is less than U2. So E1 is less than U2. Now U3 is the average of U1 and U2. So U3 lies somewhere between. Now U4 is average of U3 and U2. So this is U4. Now U5 is average of U4 and U3. U6 is average of U4 and U5. So observe that the subsequence U1, U5, the U1, U3, U5 monotone increasing, and the subsequence U2, U4, u6 are monotone decreasing, right? So these are so the odd sequence un to u2n minus 1 is increasing means upper arrow, and u2n is decreasing. Okay, now observe another thing is that from this picture it is clear that this, I mean, u1, u3, u5 all are less than u2, and u2, u4, u6 all are greater than u1. So the sequence u12 minus 1 mono increasing and bounded above, and the u2n is monotone decreasing and bounded below, right? So 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 the sequence un u12 minus bounded above, so this is, so like let's this converges to some point L1, and u2 is bounded below, so this converges some point to L2. Now if we can show that L1 is equal to L2, then we are done, because we have the following theorem which we have proved, we have written some the following theorem is that if un is a sequence of real numbers, and if even number sequence and odd number sequence goes to same, converges to same point, the whole sequence converges to same point, right? So what we have seen is that in our situation, sorry, so in our situation sequence the sequence u2n minus 1 and u2n converted. Now we only need to show that L1 is equal to L2. Okay, so how to show this? So here put 2n instead of n. So u2n plus 2, this is how much? This is half of u 2n plus 1 plus u 2n. Yeah. So yeah, u2n plus 2 half u2n plus 1 is equal to plus u2n. Now anyway, u2n plus 2 is comes under the odd term, comes under the even term sequence. So this limit, so now taking limit on the both side, we get what? We get this L2 is equal to half of u2n plus 1, its limiting value is L1 plus L2. Sorry, this must be L2. So this implies what? This implies L1 is equal to L2. So we have seen that this sequence, I mean the odd term sequence and the even term sequence converges to same point. So I mean which is L1, L and the same. So the sequence as a whole UN is convergent. Okay. So does everybody understand this? Or is there any confusion? Because it's a technical type of solution. Okay, so but
Yes.
yeah, someone is trying to speak, I think. Okay. So going to the next problem. Spells 1 second. Yeah. Suppose give a sequence even greater than 0 and assume un plus 1 is equal to 6 by 1 plus un, and un is a given sequence. So prove that subsequence is u2n minus 1 and u2n converges to common limit, and second part, find that limit. So the here the method will be same. First we try to show that even minus 1, that is even sequence, and odd term sequence firstly convergent. Then we will show that the point of convergence of these two sequences are equal, and then using it somehow we need to calculate the limit. Okay, so how to do it? So I mean, yeah, it's a first of all, it's a very technical type of solution. So just look at the screen. So first of all, just someone might think that how we can approach this. Well, first you need to solve some kind of problems regarding this, and after solving 10 to 20 problems, you will get used to the techniques or tricks that has been used in this type of problem solving. Okay, so so look at that, un plus 1 minus un. This is what? This is 6 by 1 plus un minus un. This is how much? This is 6 minus un square minus un by 1 plus un. This is 2 minus un in 3 plus un by 1 plus un. So it's some kind of middle of factor, I think. So this gives what? This gives that if un is less than 2, then un less than un plus 1, and if un is greater than 2, then un is greater than u plus 1. So if u1 is less than 2, then un is less than u1 plus 1. So, I mean, so if u1 is less than 2, say u1 is increasing, and u1 is greater than 2, u1 is decreasing. Okay, so now observe that if un less than 2, this implies un plus 1, which is equal to nothing but 6 by 1 plus un. This is greater than 2, and if un is greater than 2, the same calculation shows un plus 1 is less than 2. So this tells that if, so we have two kind of conditions. If un is less than 2, then the sequence is increasing, and moreover the next term and the terms alternatively will be less than 2, greater than 2, less than 2, greater than 2, like this. And if the un is greater than 2, then the sequence is more or decreasing, and terms are alternatively greater than 2, less than 2, greater than 2, less than 2. Okay, so if un less than 2, this implies un less than 2 less than un plus 1, and un greater than 2 implies un greater than 2 greater than u plus 1, un plus 1. So yeah, now consider un plus 2 minus un. So this is what? This is nothing but 6 into 1 plus un by 7 plus un. You can do the calculation. This is minus un. So after doing calculation, we see that this is equal to 2 minus un into 3 plus un by 7 plus un. So un is less than 2 implies un less than un plus 1, and un greater than 2 implies un greater than un plus 2. So what we have seen, we have seen that if un is less than 2, then the immediate next term is greater than un. Also, one second. Also, for the same case, the immediate next term un plus 1 is greater than 2. Also, for the same case, the term comes up with two indices, that is un plus 2. This is greater than un. So, combining this give us two cases. So, first case 1. This give what? This give that if u1 is less than 2, this implies u2 greater than 2, what we have seen, and this implies u3 less than 2, right? So this case give us u1 less than 2 less than u2. Again, u2 greater than 2 implies u3 less than 2. So this implies u2 less than 2 less than u3. So similarly, we can finally show that u3 less than 2 less than u4, and u5 less than 2 less than u4. So u1 less than 2 implies u1 less than u3, and u3 less than 2, this implies u3 less than u5, and u2 greater than 2 implies u2 greater than u4, and u4 greater than 2 implies u4 greater than u6. So altogether all these things give us u1 less than u3 less than u5 dot dot dot, and u6 less than u4 less than u2. So we have seen the sequence of odd term sequence is more increasing and bounded above, and the even term sequence is more decreasing and bounded below. So assume the odd term sequence converges from point L1 and even term sequence converges from point L2. So now we need to check that this L1, L2 are same. So how to do it? So now we have this formula that un plus 1 equals 6 by 1 plus un. So here put n equal to 2n. So we get what? un plus u2n plus 1 is equal to 6 by 1 plus u2n. So putting the limit on the both side, we get L1 is equal to 6 by 1 plus L2. Sorry. So this gives a what? So and also L2 is equal to 6 by 1 plus L1. So we have this sequence gives L1 plus L1 L2 is equal to 6, and this equation gives L2 plus L1 L2 is equal to 6. So together this thing is L1 is equal to L2. So we have seen this. We have seen that the even subsequence and the odd subsequence converging to same point. So the given sequence un is convergent. Now there is another portion which says that what is the limit? So observe that it is given that un plus 1 is equal to 6 by 1 plus un. So putting limit both sides, L equal to 6 by 1 plus L, this implies what? L square plus L minus 6 equal to 0, this implies L plus 3 into L minus 2 equal to 0. This implies L square plus, this implies either L equal to 2 or minus 3. But since the sequence even is greater than 0, so L not equal to minus 3. So the sequence converges to point plus 2. So yeah. So in this way we can solve actually this type problem. Of course this method is very tricky, but upon solving many problems you will get used to it. Okay. So this is a one time problem. So does everybody understand this or any at any
Sir,
part?
can you scroll up?
Yeah, sure. That much?
Sir, a little more.
Yeah. Up to this.
Yes, sir. Okay. Okay, sir.
Okay. So um, there is another question. I mean, there is some kind of theorem which tells that every subsequence of a monodon increasing sequence or decreasing sequence is monodon increasing or decreasing. Well, the point is that, I mean, it's a matter of common sense, right? So we have a sequence which is monotonically increasing. So obviously, any of the subsequence will be monoton increasing. So yeah, in this way you can have some intuition. That's it. And okay. Yeah, there are another. There's a good problem. Yeah. So consider the following problem. Sorry. Prove that the sequence UN is divergent. Okay? EMF 1 plus half 1/3 1 half 1/3 1/5. This is a sequence. So we need to show that this sequence is divergent. So can you tell me how to prove this? Anybody just try? So you try. I'll be back in 2 minutes. Okay. Sorry. I just yeah. So you need to the sequence is UN is 1 plus 1 half plus 1/3 plus 1 by n. You need to show that sequence is divergent. You try. I'll be back within 2 minutes. Okay. Sorry. So, have anyone? Sorry. So, have anyone tried? Anybody? So, one second. Someone's trying to join actually. So, one second. So, so u1 is equal to 1 plus half plus one third. We need to check that this is a divergent sequence. So, the way is the following. First, observe that un plus 1 minus un is equal to 1 by n, which is greater than 0. Okay. So, the sequence un is strictly increasing. Now, convergent a subsequence urn of un, her rn is equal to 1 by 12. So, what will the urn? urn is equal to 1 half 1 by 2 to the power n. This is equal to 1 half 1 third 1 fourth plus 1 fifth plus 1 by 8 plus dot 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 plus 1 by 2 to the power n minus 1 plus 1 plus 1 by 2n. So this is greater than 1 plus half plus 1 by 4 plus 1 by 4, then 1 by 8 1 by 8 1 by 8 1 by 4 times, and 1 by 2 to the power n plus 1 by 2 to the power n. Okay, so this is 1 plus half plus 2 into half square plus 4 into half cube plus 2 to the power n minus 1 plus 1 by 2 to the power n minus 1. So this gives 1 plus n by 2. So you have seen that urn is greater than 1 by n plus 2. Now the right side is divergent, so the subsequence is divergent. Now since one of its subsequence divergence, so the whole sequence diverges. That's why the summation 1 by n is a divergent sequence. So just everyone think about it for 1 minute. Let me know, is there any issue with the solution or any confusion in the solution?
Sir, is this known as the partial fraction method?
No. Partial fraction is something different. It is not partial fraction. It is known as some kind of subsequence technique or like that. Understand?
Yes, sir.
Okay. So, so yeah, it's one problem then. So, do you know about Cauchy's principle of convergence or some kind of Cauchy? Someone is trying to enter. So, do you know about Cauchy's theorem or some theorem related to convergent? Which is also related to Cauchy. So, let's discuss this. So, suppose we have a sequence un via sequence of real numbers. This is said to be Cauchy sequence if for any epsilon greater than 0, there exists m belongs to n such that mod of u um, n minus uk less than epsilon for all nk greater than or equal to m. So this is known as the Cauchy theorem of convergence. That is what is saying that for any epsilon greater than 0 we can find a capital M such that un minus uk less than epsilon. And any sequence satisfying this condition is known as the Cauchy sequence. And we have following theorem which we are not going to prove because this theorem, this proof takes a long time, but then we can't solve any problem actually. Okay, so this theorem tells that a sequence even is convergent if and only if un is a so un is a convergent if and only if un is a Cauchy sequence. It is a theorem. Okay. So, so yeah, using this theorem, if we can show that some given sequence is not Cauchy, so it is not obviously convergent. Okay. So now let's look at some kind of examples. For example, so consider the following sequence: n by n plus 1. Well, we know that this sequence converges, right? This is what? This is 1 by 1 plus 1 by n, and this converges to 1. So this sequence is a Cauchy sequence. I mean, it's a bit easy actually. It's not all right. Yeah, so the main thing is that, so well, just now we have seen that the sequence un is equal to 1 half 1 by n is divergent by the method of subsequence. So now we will see that this is divergent. We can show this in the method of Cauchy. That is, we will show that un is not Cauchy sequence. So how to prove it? So now observe that if we choose any m belongs to natural, then u2m minus um is what? This is 1 by m plus 1, 1 by m plus 2. This is 1 by 2m. So this is greater than nothing but 1 by 2m, 1 by 2m, 1 by 2m. So after doing the calculation, it gives 1. So we get what? So for half, if we choose any of the capital M, then the u2m minus um is greater than half. So the sequence un is not Cauchy. so not convergent. So in this way we can show that some given sequence is not convergent. Okay, so yeah, so it's one kind of method. And so can anybody tell me that wait a second. Can you tell me why the sequence 1 by n is Cauchy? Anybody? Why the sequence 1 minus Cauchy? Well, so we have seen this since this sequence converges to 0, so that is a convergent sequence. So convergent implies Cauchy. So and but the thing is that why the sequence minus 1 to the power n is not Cauchy. So
because
now
it's
say for
not divergent. No, no, because it's not convergent.
yeah, right, yeah, right, absolutely right. Yeah. So there another kind of problem which is suppose we have a sequence un. One. So we have a sequence un satisfying the following property. Mod un plus 2 minus un plus 1 less than equal to c into mod un plus 1 minus c1 for all n belongs to natural and for some c with 0 less than c less than 1. So un plus 2 minus, so this is the less than equal to 0. So how to show that un is a Cauchy sequence? So the method is the following. I mean, we need to show un is a sequence. So how to do it? So first observe that un plus 2 minus un plus 1. This is less than equal to c into mod un plus 1 minus c. So this is less than equal to c square into mod un minus un minus 1. So anyway, this less than dot dot less than equal to c to the power n into mod u2 minus u1. So if m greater than n, then mod um minus un less than equal to mod minus um plus 1 plus un plus 1 minus un. This is less than equal to mod u2 minus u1 c to the power m minus 2 plus c to the power m minus 3 plus dot 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 c to the power m minus 1. So this is equal to mod u2 minus u1 c to the power n minus 1 into 1 minus c to the power m minus n by 1 minus c. So this is strictly less than c to the power n minus 1 by 1 minus c mod u2 minus u1. So So now observe that this, since this sequence c to the n minus 1, this converts 0 as 0 less than c less than 1. So anyway we can make it less than epsilon for all n greater than equal to k. So this whole thing um minus u1 is less than n for all m greater than n greater than equal to k. So I mean, yeah, in this way we can show that is the causa sequence. Yeah, and there are another type of problem. Well, does everybody understand this? I mean, it's really technical. So just tell me whether is there any confusion. So okay, but if you have any confusion, I'll ask. Okay. So consider the following sequence given by un, where u1 is equal to 3 and un plus 1 is equal to 3 plus 1 by un. Show that this sequence un is Cauchy and find limit un. Yeah. So how to do it? So obviously it's a technical solution. So observe that un plus 2 minus un plus 1. This is 1 by un plus 1 minus 1 by un. This is mod un plus 1 minus un by un plus 1 un. So if u1 is equal to 3, so u1 is equal to 3 and un greater than 3 for all n greater than 1. I mean, since un is equal to 3 plus 1 by un, that's why. So this this equality gives mod un plus 2 minus un plus 1 less than 1 by 9 un plus 1 minus un for all n. So what we have done in the last example, exactly the same process will work, and finally we can see that since here 1 by n, this thing is less than 1, so the sequence un is a Cauchy sequence, hence convergent. So, well, it's convergent, but what is the limit? So, if we assume that the L is the limit of un, so now we have the following formula given of the sequence un is equal to un plus 1 is equal to 3 plus 1 by un. So, this gives L is equal to 3 plus 1 by L, which implies L square is equal to 3L plus 1. So after the calculation, it gives that L is equal to 1 by 2, 3 plus root 30. You can just calculate it. There is nothing to do. So this is another type of problem. I mean, it's a common problem, but in some kind of different form. So, well, so till now, anybody have any confusion? I will wait for 1 minute. then we'll start some kind of Cauchy theorem in limits.
So the first part, can you explain once more?
First part. Yeah, first part was like that. That un plus 2 minus mod un. This we have seen that this is mod of un minus n by un plus 1 and un. This is a simple calculation. Then observe that the formula of un plus 1 is equal to 3 plus 1 by un. And un is given to be 3. So obviously un is greater than 3 because anyway all uns are greater than 0, right? So un is greater than 3. So this whole thing gives that. So since here it is un plus 1 into un, so un plus 2 minus un plus 1, this is less than 1 by 9 into un plus 1 minus un. You understand now?
Yes, sir.
Oh. Anybody else have any confusion, doubt? Okay, so let's go to the next topic. Which is known as um, Cauchy theorem of limits. This theorem tells that if we have a sequence un, if it is a given sequence, and if we are given that the sequence un goes to L, then the average, that is u1 plus u2 plus un plus n, this goes to L as n tending to infinity. This is the Cauchy's first limit theorem. We are not going into proof, we will see some kind of application of this. Okay. So this theorem directly tells that if the sequence, main sequence un is convergent to some point, then the average sequence will be convergent. That's it. So and like for example, consider the sequence 1 by n. One second, someone is trying to join. So so we know that sequence 1 by n converges to 0. So by this limit theorem, 1 plus half plus 1 by n, this converges to 0 as n tending to infinity. Okay. So in this way we can show this. Yeah. So yeah, next. So for example, uh, so consider un is equal to n to the power 1 by n. Then find 1 plus root 2 plus cube root of 3 plus fourth root of 4 plus nth root of n. So can anyone tell what will be this value of the limit? Anybody? Okay, so So, I mean, yeah, here we need to use the Cauchy first limit theorem. Now, observe that we have seen in the uh, last week lab session that limit of n to the power 1 by n is equal to 1. So, by Cauchy's first limit theorem, this limit is equal to 1. Yeah. So, this kind of calculate this kind of limit actually helpful for the Cauchy's first limit theorem. So, another example. Un so un is a real sequence so the un greater than 0 for all n. So it is it is not an example, it's a theorem actually. Okay, first it's the theorem, sorry, it's my mistake. Suppose un be a real sequence such that un greater than 0 for all n, and limit un plus 1 is by un is equal to L, which is not equal to 0. Then show that nth root of un, it's not sure, it's a theorem says that nth root of un, this goes to L. So what this theorem is saying, this theorem, if we have a sequence un of real numbers such that terms are positive, and if the un plus 1 by un converges to L, which is non-zero, then nth root of un will convert this to L. This is known as the Cauchy's second limit theorem. So let's see some kind of application. So calculate the limit. Show that this limit n to the power 1 by n is equal to 1. So can somebody try? I will tell you after 1 minute, but somebody else try how to use the theorem written on the first portion in order to solve this exercise. Anybody try? Okay, so sure. So nth root of n is equal to 1, we need to check it. So now we want to use the theorem that if limit of un plus 1 by un is L, the nth root of un is L. So how we can do it? How we can use it? So take un equal to n. So then observe that un plus 1 by un, this is what this is, n plus 1 by n, right? And this converges to 1. So by the previous theorem, theorem in the upper portion, nth root of un, this is equal to 1, its limiting value is 1. So limit n tending to infinity, nth root of un is equal to 1. So in this way we can show that limit n to the power 1 by n is equal to 1. In the previous session we have seen that it can be, we can prove it in some other way which is very difficult and technical, but this theorem makes our life easy. So does everybody understand this proof? If not, then raise your hand.
Sir, can you explain the last part after n plus 1 by n tends to 1? After that.
Yeah. So first look at the theorem. It says what? It says that if un is equal to real numbers or positive real numbers, and if the limit of the limiting value of un plus 1 by un is L, then nth root of un this sequence will converge to n. So we have assumed un to be n. So we have seen that un plus 1 by un, this converges to 1. So due to that theorem, nth root of un will be 1, right?
Yes, sir.
So then un, we have chosen un to be n. So nth root of n is equal to 1.
Okay, sir.
So wait. Yeah, so there is another type of question. I mean, it's a direct application. Prove that limit n tending to infinity n factorial to the 1 by n is equal to 1 by. You need to check that n factorial to the 1 by n is equal to 1 by. So just asking one thing, have you done this type of limit calculation in your class 11 or class 12? Have you done this type of calculation in your class 12 or 11? Because it's kind of a J problem. Okay, I think not. So yeah, so we will use the Cauchy's second limit theorem in order to prove this. So assume un to be n factorial by n to the power. Okay. Now let's look at what is un plus 1 by un. This is nothing but n plus 1 factorial by n plus n by n factorial n to the power. This is equal to what? This is equal to n plus 1 factorial by n factorial into n to the power n I n plus 1 to the power n plus 1. This is what? This is uh, n plus 2 factorial by n plus 2 to the power n into n to the power n minus 1 by n minus 1 factorial. So yeah, second calculations to here. Real by oh sorry, I had a mistake. So this is n plus 1 factorial by n factorial. This is obviously only n plus 1 into n to the power n by n plus 1 to the power n plus 1. So this is n to the power n by n plus 1 to the power n. So this whole calculation gives this is 1 plus 1 by n to the power n, and we know it, this is 1 by e. So the nth root of un goes to 1 by e, that is n factorial to the power 1 by n goes to 1 by e. Does everybody understand this calculation?
Yes, sir.
Okay. So So we have the following problem. So xn is a Cauchy sequence in R, and yn is just a sequence in R, such that mod xn minus 1 less than 1 by n for n. Then show that yn is a Cauchy sequence and limit xn is equal to limit yn. So just can anybody tell how to solve this type of problem? Just try at least for 1 minute. Anybody want to try? Just try it out. Okay, so first of all, we need to do some kind of guess. Okay. So, so how to do it? Observe one thing that if we apply the limit entity mod xn minus yn is equal to 0, then we get this 0. This means what? That for sufficiently large n, the xn and yn distance coming very close. So from this we can guess that if it's a possible guess, if xn goes to L, then yn goes to L. So how to prove our guess is correct? So yn goes to L, we need to show. So choose epsilon greater than 0. Then observe that mod yn minus L. This is nothing but we can write it mod yn minus xn plus xn minus L. This is less than equal to mod yn minus xn plus xn minus L. This is less than 1 by n plus mod xn minus L. So this is less than 1 by n plus mod plus epsilon for all n greater than equal to k. Now since right hand side goes to 0 as n tend to infinity, so the sequence yn goes to L. So do you understand this? Each and every step? Let me know. So do you understand each and every step? So then in the problem, what is it? Yeah, so consider the following. A sequence UN is such that every subsequence of UN has a subsequence associated. So we need to show that the sequence UN is such that it is given that each subsequence of UN has a subsequence that converges to 0. So prove that UN goes to 0. So how to prove it? Anybody? Any possible guess? So, um, so I mean, if UN does not converge to 0, I mean, first of all, we need to check the UN is convergent. Then we can show that UN is. So assume that UN is divergent. So assume UN is divergent. So means what? The average epsilon not greater than 0 such that mod UN, that is an divergent means for any L in constant real number, mod UN minus L, this is greater than equal to epsilon naught. Uh, that is for all n belongs to M, we can find epsilon naught greater than 0, so mod UN less than L greater than epsilon naught for all n greater than equal to M. So this implies what? So itself, I mean, we can consider the subsequence um plus 1 dot dot dot. So this subsequence is divergent, but this hypothesis tells that this has a subsequence that converges 0. This implies what? U sum Rn minus n greater than equal to epsilon for all n greater than equal to sum n naught. So I mean, obviously some kind of m. So this subsequence URN is a subsequence of UM, but this minus L greater than epsilon naught. This means this URN does not converge to L. So since L was arbitrary. So this UN subsequence is divergent, but our condition says that it converges. So our assumption is wrong. That's why UN converges to 0. So one minute. Yeah, so consider following. Prove that limit n tend to infinity 1 plus 1 third plus 1 fifth plus 1 by 2n plus 1 by 2n plus 1 equal to 0. we need to prove this. So now can anybody tell how to approach this type of problem? Any possible guess? So in order to solve this type of problem, need to use Cauchy first limit theorem. Okay, so how? Observe that limit n tending to infinity 1 by 2n plus 1 is equal to 0. So directly by putting Cauchy's first limit theorem, 1 plus 1 third plus 1 fifth dot 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 1 by 2n plus 1 by 2n plus 1 convert as 0 as n tending to infinity. So in this way we can solve this type of problems. Okay. So yeah, that's so another kind of problem. There is some important kind of sequences. Show that 1 plus 1 by n whole to the power n. This is a monotone increasing sequence. And so obviously I think that everybody had seen this sequence before, right? In class 11 or 12, I guess. So, well, we know that this sequence has the limit e, but we know this, but here we are going to show that this sequence is convergent and we are going to define its limit to be e. Okay. So, so consider un to be 1 plus, sorry, un to be 1 plus 1 by n whole to the power n. Then un plus 1 is equal to 1 plus 1 by n plus 1 whole to the power n plus 1, obviously. So now consider the following n plus 1 natural numbers: 1 plus 1 by n, 1 plus 1 by n, all are same 1 plus 1 by n, total n times, and 1. Now use am greater than or equal to jm inequality. This gives that n into 1 plus 1 by n plus 1 by n plus 1 greater than or equal to 1 plus 1 by n to the power n by n plus 1. So this indeed give us 1 plus 1 by n plus 1 to the power n plus 1 greater than or equal to 1 plus 1 by n to the power n. This is un plus 1 and this is un, right? So what I get, that un plus 1 greater than or equal to un. So we see that this sequence un is monotonic increasing. Now we will see that this sequence is bounded above. How to check? So write un is equal to, what's the suppose try to join. So one second. So un is equal to 1 plus 1 is a binomial expansion n into n minus 1 by factorial 2 into 1 by n square plus n into n minus 1 into 2 by 1 by factorial n. One second. Someone is trying to join. By 2 dot 1 by factorial n into 1 by n to the power n. This is equal to 1 plus 1 by 1 by factorial 2 by 1 into 1 minus, I mean 1 into 1 minus 1 by n plus dot 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 plus 1 by n factorial 1 minus 1 by n 1 minus 2 by n dot dot 2 by n dot 1 by n. So this is less than 1 plus 1 plus 1 by 2 factorial plus 1 by n factorial for all n greater than 2. Now we know that n factorial greater than or equal to 2 to the power n plus 1. So it's a very well known identity. I also forgot the proof of this. You can find it, Google it, or you can look it into some kind of 11 or 12 book. Okay. So n factorial greater than or equal to 2 to the power n minus 1. So using this, it gives that 1 plus 1 plus 1 by 2 factorial plus 1 by n factorial. This is less than 1 plus 1 plus half square plus 1 by 2 to the power n minus 1 for n greater than 2. So, and also this thing equal to 1 plus 2 into 1 minus 1 by 2 to the power n. This is less than 3 for all n. So what we have seen that we started un. So un less than 3 for all n. So this implies the sequence un is bounded above. So we have seen what the sequence un is bounded above, and we have also seen that un is monotone increasing. So combining this, we get that the sequence un is convergent. Sorry. So un is convergent. So in this way, we can show that it's a converging sequence. So just let me repeat the whole argument here because it's highly technical. So what is the question? We need to show that the sequence 1 plus 1 by whole to the power is monotone is strictly increasing bounded above. So first of all, we have shown that the sequence is strictly increasing. Then we have shown that it is bounded above. So we have written un plus 1 is equal to 1 plus 1 by n plus 1 to the n plus 1. Now we consider the n times 1 into n times of 1 plus 1 by n and 1 in 1 times. So we then apply the MGF inequality, gets that n into 1 plus 1 by n plus 1 by n plus 1 greater than or equal to 1 plus 1 by n to the power n by n plus 1. So this gives 1 plus 1 by n plus 1 to the power n plus 1 greater than or equal to 1 plus 1 by to the power n. So this is equal to un. So this tells that un plus 1 greater than or equal to un. So un is a monotone increasing. So what is un? Un is equal to 1 plus 1. Now this is the binomial expansion of un. One plus one plus n into n minus one by factorial 2 into 1 by n square plus dot 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 n into n minus 1 by factorial n 2 into 1 dot 1 by n to the power n. So this is after doing some kind of calculation, we get that this un is less than 1 plus 1 plus 1 by factorial 2 plus dot 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 1 by factorial n greater than or equal to 2. Now we have the inequality that n factorial greater than or equal to 2 to the power n minus 1. So using this inequality, we see that this whole thing is less than some 1 plus 2 into 1 minus 1 by 2 whole divided, which is less than 3. So we see that un is less than 3 for all n. So un is bounded above. Hence un is convergent. So un is convergent, we get. So un converges some l. Now one can ask to prove that l is equal to e. So it comes in the difference, it goes in a different direction. So let's not get into the fact that it is actually our chosen exponential e. Okay, so yeah, so there is another kind of question. So just first let me know, does everybody understand this solution? Does everybody understand the solution? So let's get into the next problem. So consider the sequence xn, where this xn is given by 1 plus 1 by 1 factorial plus 1 by 2 factorial plus dotted 1 by n factorial. It's a monotone increasing sequence. And bounded above. And this limit, we will show that this limit is actually our exponential. So how to solve these two problems? First, we show that this is a monotone increasing bounded above. So xn plus 1 minus xn, it is basically 1 by n plus 1 factorial. This is greater than 0. So the sequence xn is a monotone increasing. Now observe one thing, that xn is equal to 1 plus 1 plus 1 by 2 factorial plus dot 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 1 by factorial. This thing is less than 1 plus 1 plus 1 by 2 plus 1 by 2 squared plus 1 by 2 to the power n minus 1, because n factorial greater than or equal to 2 to the power n minus 1. So this is equal to 1 plus 2 into 1 minus 1 by 2 to the power n. This is less than 3. So xn is less than 3. So this is monotone increasing, and this is bounded above. So it is bounded above. So xn is convergent. Now we will see that this limit is e. So this requires some kind of techniques. Okay. So yeah. So first assume that un is equal to 1 plus 1 by n whole to the power n. So then un is equal to, doing the binomial expansion, 1 plus 1 n into n minus 1 by 2 into n square plus dot 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 n into n minus 1 dot 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 2 into 1 by factorial n by 1 by n to the power n. This is equal to 1 plus 1 by 1 plus n factorial into 1 minus 1 by n plus 1 by factorial n into 1 minus n into 1 minus 2 by n dot 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 2 by n into 1 by n. This is less than 1 plus 1 1 by 2 factorial 1 by n factorial for all n greater than equal to 2. So limit un greater than equal to limit xn. This is what our xn, right? So limiting value un less than equal to limiting value of xn. Now limiting value un is assumed to be exponential e. So e less than equal to limit xn. This is one side of inequality, and for the other side, for the other side, choose m and n such that n greater than m, and then un is equal to 1 plus 1 plus 1 by 2 factorial into 1 minus 2 square plus 1 by 3 factorial into 1 minus 1/3 into 1 minus half plus dot 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 1 by m factorial into 1 minus 1 by n 1 minus 2 by n dot 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 1 minus n minus 1 by n plus dot dot dot. So I mean, after doing the calculation, you will see that this is greater than 1 plus 1 plus 1 by 2 factorial into 1 minus 1 by n plus dot 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 1 by n factorial. So 1 by n multiplied all by 1 minus m minus 1 by n. So now here keep m fixed and let n tend to infinity. Assume that limit n tend to infinity when greater than equal to 1 plus 1 1 by 2 factorial plus 1 by n factorial, or this gives e greater than equal to limit of xn. So we have already got some previously e less than limit of n, and now we get that e greater than equal to limit of xn. So limit xn is equal to e. So yeah. So does everybody understand this, or I will repeat the whole solution rigorously?
Can you repeat that un equal to the lower bound when you're proving 1 plus 1 plus 1 by 2 factorial into 1 minus? Those two steps, can you tell us again?
Yeah. This is step, right?
Yeah, the lower bound, proving the lower bound part.
Yeah. So, yeah. So look at the un. So this is the binomial expansion of un in the first line. In the second line, I just cancel one of n and keep that 1n inside the bracket. So it is 1 by 2 factorial into 1 minus 1 y plus and dot the same by same type of argument 1 by n factorial into 1 minus 1 by n into 1 minus 2 by n dot 2 by n into 1 by n. Now obviously this is less than 1 plus 1 plus 1 by 2 factorial because 1 minus 1 by n it is anyway less than 1. And
Yeah,
last
this is fine. The other one, that other part.
other.
Yeah.
So this is un is equal to
Yeah.
un is equal to this. So is 1 plus 1 plus 1 by 2 factorial into 1 minus half square plus 1 by 3 factorial into 1 minus 1 by 3 into 1 minus half. So yeah. So
How?
yeah, I think about it. Yeah, because uh,
Okay. Yeah,
it's,
fine. Yeah, 1
essentially
minus 1 by n square. Yeah, I got it.
I
Yeah, it's fine.
remember the name of the
Yeah.
formula. Okay.
Huh?
I mean, this formula it has a certain name, but I couldn't remember it actually.
No, it's fine. So you have n into n minus 1 into 1 by n square, no?
Yeah.
So 1 by 2 factorial, if you take out n into n minus 1 by n square will become 1 minus 1 by n square.
Yeah,
That
right.
you will get 1 minus 1 by 2 square and so on. Yeah, sorry. Yeah, it's fine.
So there
Yeah,
will be
continue. Sorry. Yeah.
no, sure. So there is another similar kind of problem. Says that show that plus 1 by n to the power n plus 1 is a monotone decreasing sequence. Yeah, we need to show that the sequence 1 plus 1 by 2 to the n plus 1 is a monotone decreasing sequence. Okay. So how we can prove it? So the technique is same. Choose Vn to be 1 plus 1 by n to the power n plus 1 and consider the numbers n plus 2 in the numbers. So 1 minus 1 by n, 1 minus 1 by n plus 1 dot 1 minus 1 plus 1. Total, this in total n plus 1 times and an extra 1. So then apply am greater than gm gives n plus 1 into 1 minus 1 by n plus 1 plus 1 by n plus 2 greater than 1 minus n plus 1 plus n plus 1 to the n plus 2. It's direct comes to mgm inequality. So this calculation gives that n plus 1 by n plus 2 to the power n plus 2 greater than n by n plus 1 to the power n plus 1. So further simplification gives that n plus 1 by n to the power n plus 1, then n plus 2 by n plus 1 to the power n plus 2. This implies 1 plus 1 by n to the power n plus 1 to 1 plus 1 by n plus 1 to the power n plus 2. So this is what? This Vn greater than or equal to Vn plus 1. So the sequence Vn is monotonic. So in this way, we can show that this sequence Vn is monodecreasing. So
Can you just show the question?
yeah, sure. The question is that uh, show that a sequence 1 plus 1 by n to the power n plus 1 is a monotone decreasing sequence. So what we've done that a second. So what we've done is that if Vn is equal to 1 plus 1 by 2 to the power n plus 1, then we choose first, we need to use the AMGM inequality, which is like 1 minus 1 by n plus 1, comma 1 minus 1 by n plus 1, dot, dot, 1 minus 1 by n plus 1, this is n plus 1 times and 1. So use the AMGM inequality, it gives that n plus 1 into 1 minus 1 by n plus 1 plus 1 by n plus 2, this is greater than 1 minus 1 by n plus 1 to the power n plus 1 by n plus 2. So this gives us what? So this gives us n plus 1 by n plus 2 to the power n plus 1 greater than n by n plus 1 to the power n plus 1. And this gives n plus 1 by n to the power n plus 1 greater than n plus 2 by n plus 1 to the power n plus 2. So after the calculation, we can see that this is Vn greater than or equal to Vn plus 1. So, I mean, yeah, we can show that limit is identity, but for today we are not going to discuss. So the main two thing is that we have seen that factorial 1 by n equal to 1 to infinity, this converges to the limit e, and this is nothing but limit n tending to infinity 1 plus 1 by to the power n. Now just tell me one thing, do you know the summation 1 n equal to 1 to infinity? I mean, what does it mean? Not intuitive meaning, it's mathematical meaning. It means that what does the series 1 plus 1 by n factorial plus 1 by 2 factorial plus dot 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 1 by n factorial, where the series converge. So we have, so I mean, yeah, when we'll discuss about series, we will, I mean, we must have, so we must see the definition. So this still holds. So it's this nothing but a generalization of the fact that ln of 1 plus x is equal to 1 plus x squared by 2 factorial plus x cubed by 3 factorial plus and dot dot dot. You must have seen this type formula in your class 12, right? So just for yeah. So here if you put n equal to 1, so ln is 1, that's it. So and the main technical tool is the MCT, that is the monotone convergence theorem, which tells that if we have a sequence which is bounded above and monotone increasing, then it is convergent. Also, if it is bounded below and monotone decreasing, then it is divergent. Yeah. So that's it for today. So yeah, that's for today. Do you have any question? You can ask.
Sir, can you just give the link of the YouTube because we have not got it yet.
I mean, I will first up. 1 second. I mean, you can access it in the Bharti ma'am. Okay. I mean, if you will not get, then in next a week I will share. Okay.
Okay, sir. Okay, okay.
Okay. Thank you.
And sir, can you just read any book for real analysis?
Sorry.
like, can you just suggest any book for reading of real analysis?
Yeah, there is one book, namely Goldberg. Have you heard about this book? Goldberg Analysis. This is a very good book. You can go through it, and this book is written in very simple language. Okay.
Okay, sir.
Okay. Thank you. So I'm in the meeting. Okay.
Okay, sir.